Welcome to this lecture. In the last lecture, we had towards the end we were discussing about representing complex processing logic. If we write the complex processing logic in the form of a text description, then it becomes difficult for the developers to understand, for the testers to develop test cases, and also it is very likely that in a text based description of a processing logic, certain combinations of conditions or variables and their corresponding action might get missed. And therefore, it is a good idea that during requirement specification, if we find that the logic is slightly complex, then we have to represent it in the form of a decision tree and table. We had seen that these are very simple semi-formal techniques, and we can very easily develop the decision tree and decision table for any problem. Let us take an exercise. We want to develop decision table and decision tree for the following problem. Let us see here that the problem statement is very simple, but still the developers and testers might find it bit confusing. If the flight is more than half full and the ticket cost on the flight is more than 3000 rupees, then free meals are served, but in domestic flight this rule does not apply, and all meals are charged on all domestic flights. So, if you can see here the conditions here, that one is that whether the flight is the one of the conditions here is that whether the flight is a domestic flight. So, let me just write here the flight is it domestic, yes or no, and then another condition is that ticket cost greater than 3000 or not, and then we have to check whether the flight is half full, occupancy greater than 50%, occupancy greater than 50%. If it is a domestic flight, then free meal, these are the actions, free meal or charge meal. If it is a domestic flight, then these are does not matter, we will have to charge the meal. But if the flight is not domestic and the ticket cost is let us say less than 3000, then these do not matter, it will be charge meal. If the flight is not a domestic flight and the ticket cost is more than 3000 and occupancy rate is less than 50%, then again we charge the meal. But if it is not a domestic flight and the ticket cost is more than 3000 and the occupancy is also more than 50%, then we give free meal. So, As you can see here that this gives a very conceptually meaningful representation of these conditions. But then remember that this is still a rather simple condition that we are trying to represent here as an example, but the conditions can become much more complex and therefore, the true use of a decision table can come out. I leave it to you as exercise to develop the decision tree representation for the same problem. Now, let us conclude our discussion on requirement specification and let us proceed to look at software design aspects, because typically in the life cycle after requirements design tasks are taken up. We will start with some very basic issues in software design and then we will look at the procedural and object oriented design principles. We will look at now software design and we will start with some very basic issues in software design. The design activities are undertaken once the requirement is complete. SRS document is written in the traditional models. During the design phase, we have the SRS document as the input and then do some activities during the design and then we come up with a design document at the end of the design phase. The design document can then be taken up and coding can start, and our design document is good if the coders can just take it, the programmers can take it and can start writing the code easily. This is just a graphic representation that during the design phase, so this is the design phase, and the input is the SRS document. We perform some design activities and then at the end of the phase we have the design document. Now, let us see at the end of the design phase what are the documents we should have with us, what we should prepare during the design phase, and then we will address the question how to prepare those. Typically, we have the module structure in a procedural design or the class structure in object oriented design, the control relationship among the modules, this is in a procedural design, and similarly in a object oriented design we have the invocation sequences among different classes. So, this is the call relationship or invocation relationship between the modules or the classes. The interface, that is what data exactly is given as a parameter when there is a call, function call or a method call, that we call as the interface among the modules. So, this is basically the data items that are exchanged between the modules. And also we need to design the data structures of the individual modules and also the algorithms that would be used. So, these are all the different items that must be designed during the design phase, that is the module structure, The call relationship among the modules in an object oriented way we will see little later, that this is the class structure, the invocation relationship among the classes, and then the interface among the modules, that is what parameters they pass or the data items that are exchanged among the different modules, the data structures of the individual modules, and then the algorithms for the individual modules. So far we have been referring to modules, but what exactly is a module? In a procedural implementation, a module is basically several functions and then their associated data structures which are referred by the functions. In the context of object oriented design, a module can be a class or a package. So, there are in a procedural design, a module consists of several functions and there are some global data here, maybe arrays, linked list or other structures here, and these different functions can access those global data. So, a module consists of certain data structures and also the functions, and in a procedural implementation, a module is a independently compilable unit. We can create the object code for a module, we can compile it and then later for generating the executable code, we can link the object codes for various modules. This is the call relationship among the different modules. We will see that it is a good idea, it is a good design if our module structure looks like this, a procedural implementation, it looks like a tree. As we proceed, we will understand the reasons why the module structure, the call relationship among the modules should look like a tree. Another thing that we must keep in mind is that when we try to design all the items that we discussed, the module structure, the call relationships, parameters, data structures of the individual modules, algorithms to be used and so on. It is never come as a single sequence of steps. Design is a very intellectually stimulating work and need to do several iterations. So, as we look at the procedural and the object oriented design, we will see that we will have to iterate over several steps, look at evaluate design alternatives and then we will come up with a good design. Now, let us look at what are the stages in the design. There are two main stages in the design phase. One is called as the high level design or the preliminary design, and the other is called as the detailed design. The high level design is also called as architectural design, and then we have the detailed design. So, it is a preliminary or high level design or architectural design, and then we have the detailed design. As we will see that there is a significant difference in the steps in the procedural and object oriented design, and the meaning and scope of these two vary quite widely between procedural and object oriented design, the architectural design and the detailed design. Even in the procedural design there are several methodologies. We look at one of the methodologies, but there exist dozens of methodologies. Even among the methodologies, there is quite a variation in what exactly should be done in the architectural design and what exactly to be done in the detailed design. We will look at those issues little later, but then let us see what is expected in the high level design. In the high level design, after we complete this task, we should have come up with the module structure. What are the modules in our implementation and their call relationships and the interfaces between the modules. But then how do we come up with the modules? How do we determine their call structure and what are the parameters to be exchanged, that we will discuss subsequently. The high level design is also called as the software architecture. One of the popular notations for representing the high level design is a structure chart. Structure chart essentially looks like what we had drawn earlier, intuitively very straightforward. It looks like a tree structure with modules as rectangles and so on. We will look at the structure chart representation of the high level design and how to come up with the structure chart representation, that we will address next, that is after this lecture. But then the structure chart is not the only representation that is possible for the high level design. There are many other notations, for example, Jackson diagram, Vernier diagram and so on. Once the high level design is complete or the architectural design is complete, take up the detailed design. In detailed design, we look at what are the modules that has been identified during the high level design, and then for each of the module need to design the data structure and also the algorithms to be used. The outcome of the detailed design is called as a module specification. This is a module specification. There are various notations for module specification. It can be a simple text based notation, informal notation. It can be slightly semi formal notation, where represent the data structures and the algorithms. But so far we just looked at some simple concepts, that during design we need to have the high level or the architectural design, that is the first step, and once the architectural design is complete, we have the module structure, call invocation, call structure, the invocation among the different modules and the interfaces among modules, that is the data exchange between different modules. And we represent that in a tree like diagram, a structure chart or something. And after that, take up the detailed design, where we design the data structures of the individual modules and also the algorithms. But then let us try to understand a very fundamental question, that let us say you have come up with a design, a tree like diagram you have represented, come up with a module specification, but then how do we know that whether your design is good or bad, or what should be the target of any design methodology to come up with a ideal design? Because unless we know that what we mean by a good software design, even if we have given to learn the methodologies of design and so on, we will not come up with a good design, because ourselves before design we have to be clear about what is meant by a good design. Unless we understand that issue, that what is a good design, we cannot come up with a good design, even if we use the most sophisticated tools and design methodologies. Another reason why we must know about good designs is that we must be able to distinguish between good and bad designs, or in other words, we should be able to evaluate between design alternatives. During the various design steps, we will see that there are alternate solutions are possible. We should be able to take the better ones, because it is not a unique way to design a software. We will see that it is always evaluating between alternatives, and for evaluating between alternatives, we need to distinguish between which is a better design and which is a inferior design. The first thing is that another reason is that different developers, by using the same methodology, they can come with very different designs at the end. We should know, we should be able to tell how good is the design, or we can select the better design if we have different designers come up with different designs. So, let us now address this important question, that what is a good software design. We will answer this very conceptually. The first characteristic of a good software design, that it should have addressed all the requirements that were there in the requirements document. That is, it should implement all functionalities of the system as specified in the SRS document correctly. So, the functionalities etcetera should have been correctly understood, and our design should be as per the requirement. Okay, that is at least the basic requirement. Unless the design is correct, it is no good. The second characteristics of a good design is that it should be easily understandable. It should not look like a messy structure and somebody spends days, months or years trying to understand the design. It should be an elegant design, and somebody looks at the design should be able to easily understand the design. Understandability is a major characteristic of a good software design. Of course, it should result in an efficient solution, and another characteristic may be that should be able to change the design easily, because during development lot of changes happen, requirements change, and based on the design change, and even after the development the software continues to change, and therefore, our design should be such that we would be able to change any part of the software, and that helps in maintaining the software. But we have highlighted one aspect here, is that the design should be easily understandable, and it turns out that this is one of the most important characteristic of a good software design, that it should be easily understandable. The main reason why we consider understandability of a design is a major issue is that unless somebody able to understand the design, it will, you cannot write code for that, and also becomes very difficult later to maintain the design, because the maintainers, for them to understand the design would become very difficult, and they cannot change, they won't know where to change, what to change, etc. So, and also we had said that maintenance is a major concern, because majority of the effort and cost is incurred in the maintenance work compared to the development work, or you can say that development work is a fraction of the maintenance work. And therefore, while writing any software, maintenance, whether it is maintainable, is a major concern, and to facilitate maintenance we have to develop design which is simple to understand, code which is simple to understand. Understandability of the design is a major issue, requires significant attention by the developers, the designers, and also every design methodology helps to come up with good design which is easily understandable. Majority of the effort spent on maintenance, and therefore, unless it is understandable, design is understandable, maintenance effort will become extremely expensive. But the next question that we will answer is that how to improve understandability, or how do we come up with a design which has good understandability. First, let us agree that one of the most desirable characteristic of any design solution is that it should be very easy to understand, and then we will have to address the question that how do we come up with a design that has good understandability. This is a issue which has some details that we must understand, and in the next lecture we will address this very basic issue that how does one come up with a design that will have good understandability. We will stop here and continue in the next lecture.